So, uh, as is often the case, when you're going to talk about the future, you often find yourself talking a little bit nostalgically about the past. So you have to sort of look back to where network service mesh came from. And it started with a very basic dream. And the dream was to be able to solve the unsolved L2, L3 problems in Kubernetes in a cloud native way. Now, and part of what made this challenging was Kubernetes networking is actually incredibly well done for a very large set of the use cases that people might want to do. So for most of the users of Kubernetes networking, there actually wasn't a problem. And the vast majority of the solutions that were being proposed to try and extend it to be able to solve broader sets of problems actually were a problem. They involved importing very antiquated models of how you do networking from Cloud 1.0 into Kubernetes. And that ended up not being a viable path. And so network service mesh was sort of born from a very basic plan. Borrow the ideas from application service meshes, things like Istio, Linkerd, et cetera, and apply them to the L2, L3 payloads that we were familiar with from broader networking. And so you start with the most basic notion, which is any service mesh you have has a service registry, in our case, a network service registry, where you keep a list of your services and the endpoints that provide those services and various metadata associated with those. And so the very first people we hit when we went to try and do this is, unlike when you're trying to write an application service mesh on top of a HTTP web proxy, there's no one true connection protocol like TCP for things that carry L2 and L3 payloads. So we created one. We created a gRPC API to, in a very generic sense, let us say, look, we'd like a virtual wire that connects us to a network service, and we'd like to be able to ask for it and get it. We'd like to be able to close it, and we'd like to be able to tell what we actually have going on. And this actually worked remarkably well. So we spun up the network service mesh repo, people started contributing, forward progress was being made. Stuff started working. So we had a lot of CI up and going, doing continuous integration. That CI was running on GKE, EKS, AKS, vanilla Kubernetes. Everything was working pretty well. And then we realized that this is actually bigger than a single cluster problem, right? The real power of it actually comes in being able to conceptualize network services as things that are not attached to your particular cluster. Floating network service domains that different workloads at the granularity of workloads can connect to. And in fact, we went on further to realize this is bigger than just Kubernetes either, because the same tricks that we use with network service mesh for allowing individual workloads to get precisely the network services they need, independent of where they're running, also extend equally well to VMs and on-prem services, on-prem servers. But then complexity grew. As you actually try and do things in Kubernetes, you discover that you need more components than just endpoints that provide services and clients that consume them. We needed things like the network service manager to allow us to have a single point of conversation there. We needed things like Forwarder to handle like very pedestrian things like cross connects, where one side wants a kernel interface, the other side wants an MIF or a VXLAN. And so the components started proliferating, which is not necessarily so bad. But the worst problem was that the API started proliferating, right? So what had started as a very simple API to stick things in the registry and to ask for network services, picked up things that were similar in form, but to go and program cross connects into forwarders. And this worked, but it introduced a lot more complexity into the system. You can sort of see here the diagram of how this went. The network service client would ask for something, the network service manager would find the network service endpoint and request the network service from it, get back the parameters, and then we'd have an entirely different API that programmed the forwarder, and we didn't actually know anything other than what we've been told in the forwarder registered when we did this, and we didn't have any terribly good way to bring in multiple forwarders, and there was definitely a lot of interest in having multiple forwarders, because as it turns out, there are a lot of approaches to that part of the problem, and they all have different pros and cons to them. And so you want to be able to support them, not just as choose one of these, but as a take whatever set of them, actually solve your problem. And that was the first point at which we realized that a little bit of simplification was going to be needed. And that was not supposed to go there. Why? Oh, hang on. Let me, are you guys seeing this presented or?
Yes, we saw.
Right, I'm back.
Yes.
Yep, cool. And then the last thing that happened was, so we got the API proliferation. From there, we started noticing other things, like the CI had slowed down, right? So it was now taking an hour and 40 minutes or so to do a CI run every time you pushed a patch, and this is wholly unacceptable. It also started getting hard to add new features to the system because there were so many pieces that were just slightly different in their API to deal with, and so many components in the system. We proliferated a bunch of internal APIs. Turns out internal APIs make things very hard to evolve, etc. And so we went and took a look at doing a simplification. And it turns out simplicity is a almost unalloyed good. Simple systems tend to be robust, they tend to be resilient, they tend to be secure. And so you want to try and keep your entire system as simple as you possibly can, but no simpler. And so looking around, we realized that fundamentally there are only really three kinds of things in the network service mesh world. No matter how many different kinds of components we had, everything was either a network service registry, someplace where you scribe down the network services and their endpoints, or it was a network service client, something which wanted a virtual wire to a network service, or it was a network service endpoint, something which was involved in providing a network service to a client. And so from that, we could clearly see that the fewer APIs was going to be better, right? So the network service endpoint was going to need to register and unregister with the network service registry. The network service client was going to need to potentially find, or something on its behalf was going to have to find, network services from the network service registry. And then our old familiar request, close, and monitor were still there, but it was all request, close, and monitor a connection for a network service. And this also made it easy to secure, because if you construct it this way, you can basically bring in SPIFFE, Spire, and OPA to secure these conversations, because they're very primitive conversations, and they're potentially pairwise conversations. So your network service client and endpoint could both have cryptographically authenticatable identities, and you could use Open Policy Agent in your network service endpoint in order to actually restrict which clients were allowed to talk to that endpoint. You would likewise use that to restrict which clients were allowed to look things up on the registry if you needed to, and what's allowed to register or unregister for a particular service. And this also ended up making it easy to heal. In the first turn of the crank with network service mesh, we had a fairly robust healing process. You could kill any one component in the system. You could kill off the network service manager on a node and it would restart, and then everything would be fine, or you get good recovery of the system state. Same with the forwarder, or the remote network service manager, or the network service endpoint. You would lose any one component in the system, and its neighbors could reconstruct the state that you had lost, and you could restore exactly what you were looking for. But as the number of components proliferated and the number of APIs proliferated, this got to be quite complicated. And we were still at a place where we could only lose one piece of the system at a time. And so in looking at resilience and healing, it turns out that the best way we could find to approach this was to say, from the client to the endpoint, the client should monitor to detect if the endpoint doesn't believe it has a connection for that client, and if it doesn't, re-request. The endpoint should expect to receive a refresh from the client before some expiration time for that connection. And if it doesn't, it cleans up resources by closing connections. And likewise, when you're talking about registering endpoints, you should expect registration to use the endpoint to use find to detect when the registration is missing and re-register itself. And likewise, the registry should, after some expiration time, if it doesn't receive a refresh of its registration from the endpoint, should simply remove that entry from the registry. When you set the system up this way, it's a fairly clean and simple set of fast healing together with acceptable levels of cleanup of resources over time. And essentially this basic pattern becomes whatever client in the system you have, it detects failure fast and it repeats the request. If all the requests have expirations and the client repeats the request before it expires. So it becomes literally impossible for the server to tell the difference between a refresh of a request and a heal request. And then the server just needs to eventually clean up any expired state that it's accumulated, whether that's a connection for a vWire or a registration in the network service registry. But this is all well and good when you're talking about pairs of things. But number one, people really like the fact that you can compose network service endpoints together to form a network service. And number two, it turns out the world is actually more complicated than simple pairwise behaviors. So for example, you probably, if you're a normal pod on a Kubernetes node, need a little bit of help getting off the node because there are things that are required to get off the node as part of the network service mesh that require privilege. And we don't want every single workload to be privileged. And the approach to this then is you get to complexity by composition of the same pattern again and again and again. So your client asks an endpoint, which may itself be a client, which asks an endpoint, which may itself be a client, all the way down the line. And a network service endpoint may or may not, as part of the work that it's doing to help you get what you want, have a data plane associated with it. So for example, if you look at the Kubernetes case, you've got a network service client sidecar in your workload pod. The network service manager primarily is actually not shepherding a data plane. It's doing very basic work around trying to resolve what network service endpoints you might be dealing with, what forwarders you might be going through, et cetera. This is very similar to the observation earlier today in a previous talk where they were pointing out that you actually could have network service endpoints that did not actually have data plane pieces themselves. Now, this does introduce one wrinkle to healing, because you would like to be able to heal in such a way that if you lose some element in the system, say if your network service manager restarts, you would like to be able to get back as close to what you had before as possible. And the way that we accomplish this going forward is with paths. And a path is very simply a repeated set of path segments and the index for where we are. So every time you get a request going along the hops between these NSEs, it has a notion of where it is in the path, and you have, for each path segment, the name of the entity, the network service endpoint that was in the path, or client, whatever ID it uses locally, a token that can be used so that it can authenticate when something is presented to it for refresh, whether it should permit things to go forward, at a timestamp that gives you expiration. Additionally, we realized that it's very helpful to have the metrics associated with each hop on the path, so that, for example, if I have a network service client running in a cluster that ends up going through many hands on the way to a network service that's running, say, in another cluster, in another zone, in another public cloud, that I can actually get metrics that tell me exactly where along that path things have broken down. Makes the entire system substantially more debuggable. The next thing that became very clear was we needed to improve our modularity. So we already had an SDK, and as far as it went it did fairly well. You actually have seen people use some of the internal tracing bits that it has in their applications for Jaeger, just to sort of see where things happen. But we wanted to take it sort of to the next level. And essentially what we ended up doing was building out chain elements that did all the pedestrian bits that you don't necessarily want to do when you're writing your network service endpoint. So it's probably not the case that you want to handle the basics of path updates, token updates, timeouts inside the server that you're writing. you have a bunch of stuff that here we've labeled as additional functionality that you basically would like to have those be the pieces you work on. And so, for example, we have an endpoint.new service you can call, providing a small number of parameters and the list of your chain elements to do the bits of work, the programming firewalls, programming your data plane for your NSE, or whatever other interesting bits you're doing, rather than having to rewrite all the logic for everything going forward. And as we sort of expanded out, we've written a bunch of granular pieces of this. So something that plugs you in as a kernel thing or a MIF thing, for example, to VPP agent or to some other data plane. And you've got a similar sort of behavior with clients where, again, the first step anyone needs to do is to authorize. All the healing and refresh behavior is encapsulated, the update token pieces, et cetera. And it turns out this actually turns into a very powerful pattern because it means the various concerns in the system are highly localized. And because the only thing you end up doing from one is calling the next instance of the API, and it's the same API as you received, the amount of trouble you can get into with unduly binding together the pieces that you've constructed as chain elements is relatively limited and well-defined. And so it becomes very possible, and the system strongly influences you towards writing very self-contained chain elements that can be composed together in chains in order to achieve a wide variety of ends. So, in fact, I will often point out, if you look at it this way, network service mesh is actually fractal in nature as a system. Down inside an individual client or network service endpoint, you have little tiny chain elements that are calling each other through a chain. Then from there, you might have your client calling a network service endpoint that does some of the work, say some of the work to get you off the node in terms of resolution and lookups, which then calls the next component, say a forwarder on the same node to get you out of that. As you saw in the talk earlier about interdomain, as you reach the edge of your cluster or your cloud provider, you may hit another network service endpoint in there as a proxy network service manager is what they were generally called, that literally all it does is accept the call along the chain and do the next little bit of work in order to solve the problem. We also realized that part of the reason our CI was slowing down was we were trying to do absolutely everything in a single monorepo. It turns out that monorepos have a small number of advantages, particularly when you're first starting. But as you go on and on, they do have exactly the kinds of situations that we were running into. You tend to wind up with stronger coupling than you intended between components. Your CI begins to slow down. You suddenly discover that you have multiple Go modules in the same repo, or that you're actually building 7 or 8 or 9 or 10 different Docker containers in the same repo. And so we started exploring a multi-repo approach. And so the first simplest one we did was just the network service mesh API repo. It's a place to put all the APIs. It's basically some protobuf definitions and little bits of top-level NSM API. But the problem, of course, when you go to something like multi-repo is how do you keep the pieces in sync? And so the very first problem we ended up solving was how do we auto-propagate down the chain of dependencies of the repo? So for example, the SDK depends in a Go module sense on the API. So every time a change comes into the API, it will automatically push a PR to the SDK that will update the dependency version to point to the new version of the API. If that passes CI, it will be auto-merged into the SDK. If that auto-merge succeeds, you will then get PRs pushed down to various platform-dependent SDKs, things like SDK VPP agent or SDK kernel, etc., and possibly down directly to individual commands. And these individual commands are the components we know and love. They're things like command K8's network service manager or command K8's forwarder dash something. And these different command repos are those sort of individual components, but again, all of them are either service registries or NSCs at the end of the day that do some small part of the work involved in getting you what you really asked for from network service mesh. And then finally, once your commands have been built, you propagate down to various deployment mechanisms like Helm or operators, and down into integration platforms for the various places that you run and test. Things like Kubernetes on Packet, Kubernetes and GKE, EKS, AKS, et cetera. And one of the nice things about this is if you decide that there's a new environment you want to integrate against as part of your CI, say OpenShift, you simply can add another repo. The people interested in that can work on it. Things can be auto-propagated to them, and you keep moving forward. So this gives you some idea of how this impacted our CI time. So the API CI takes about 1 minute and 20 seconds to run. SDK is a little longer, it takes about 4 minutes. The platform dependent ones take about 3.5, and so on down the line. So if you're really talking about the end-to-end propagation of a change, presuming that nothing goes wrong, it's about 15 minutes end to end. But if you're just trying to make a change because you wanted to fix a comment in the API to improve it, or because you're introducing a new chain element into SDK VPP agent, you're looking at very short timeframes to get CI feedback on your patch and be able to merge it. Which of course begs the failure detection and mitigation question, which is, what do you do when things go wrong? So you start with something, say an SDK for VPP agent, and it propagates down to the various command repos, and they propagate down to the Helm and operators, and that propagates down to an integration test that fails. You can actually chase the failure back to the offending patch. Depending on the seriousness of the issue, you can go fix it upstream, or you could revert it upstream until you sort out exactly what you're going to do about it. And having put the fix in, you can add unit tests to the platform level to make sure that you don't get that particular flavor of escape again down to integration. So, questions. Well, first, special thanks to our event sponsors, Anthem and Cisco, but would love to take questions. I'm going to leave presentation mode because that lets me actually see the questions.
I put a question in the NSM Slack.
Let me go take a look.
Yeah.
So is there anything to prevent you from doing update path before authorize in the NSC example? All right, so let's go back and take a look at that particular example. And you're talking about the client.
Yeah.
So I tend to think about the world in terms, let me put it this way. Engineers are lazy. It's what we pay them for.
Yeah.
And if I give you a handy function called new client that you only have to fill in the blanks for, now you're going to generally find that almost every engineer will use it unless there's a really good reason they think they need to do something different.
I agree, but
So,
this is a set, but it should be a sequence, as I see.
I'm sorry, I didn't quite hear you.
This is an array. I mean, when you do append, you will have an array. So the functions will come in a sequence, and they are actually decided. I mean, there are some combinations here that are completely useless, so you shouldn't be able to do them. This is what I mean.
Yeah, so effectively, I have sort of a mathematician's attitude towards that, which is you can do, let me sort of put it this way. We're all engineers here. We all know that occasionally you have to do something that you really think is a bad idea in order to make something work or to deal with a problem that you did not foresee. So rather than putting very hard limits in that make it impossible, for example, to switch the order of authorize or update path, which I would not recommend, by the way. But rather than hard coding you in where you have no choices in that matter, we make it instead so that the easy path is to do them in the correct order. I mean, please note, for example, you would literally replace update path if there was some particularly good reason you needed to as a chain element. All the chain elements could in principle be replaced one by one as needed. However, it's going to make your life much harder. And going back to the engineers are lazy, it's what we pay them for. That's the fundamental social limitation on engineers doing particularly stupid things.
Yeah, I still think it should be possible to do stupid things. So it's not that. I think that the default should be more like pushed, because I remember sometimes very early in the NSM history, you reversed this list like a year or something. And we had a lot of problems with that. I mean, yeah.
Oh, okay. So I see sort of your point. I mean, part of what it comes down to is that since you have client calls, essentially one client calls the next in the chain, and then the returns go back the other direction. So part of the question becomes, are you doing work on the way in, or are you doing work based on the return?
Yeah, and can you guarantee you will do it in 2 years in the same way?
So for example, if you are writing a piece of a client that is going to plug something into a vSwitch like VPP, to plug it into the vSwitch and VPP is probably going to end up being done as part of the return part of that pass, not on the way out, because on the way out you don't actually know what your connections look like. So let's see, we had someone who raised their hand. Let me see if I can find that information. So yes, so there's a question online where Shini was asking, does this change include support for multiple data planes? It was literally motivated by the desire to support multiple data planes. That's kind of where we started.
I know.
Not just multiple data planes, but multiple simultaneous data planes.
But you have the same construct today, even in the old. I mean, if you went into a network service, you have the same. You do the composition of the IPAMs and stuff like this, you know. Yeah. But maybe it's not important. I just wanted to know, because but what you say, that the designer should be lazy and steal the code that exists and don't think too much about it.
Yeah, I mean, don't think too much unless you have a hard problem to solve. I'm very much in favor of thinking when you have a hard problem to solve. So someone raised their hand. I'm trying to figure out how that worked and who. So excellent. So, and please note, this is stuff that's been going on in the background in the community at this time. We've been building this out for a little while. Some of you have probably seen some of the pieces go by. And these pieces, as they've gone by, have been sort of very openly discussed in the community as we've gone. That said, I think we care a great deal about usability of the system. So for example, you'll find that other than the introduction of paths, which adding new fields in gRPC is relatively straightforward, you haven't seen a whole bunch of shift in terms of the semantic content of the APIs, for example. So Charles Eckel has raised his hand. Let me see if I can figure out how to unmute him. Okay, you appear to be permitted to talk, Charles. Did you want to say something?
Hello, Ed. No, actually I didn't. I don't know what I did to raise my hand, but it was an accident. So great talk, though. I appreciate it.
Cool. So we are right up against the time. I would be delighted to discuss this with folks in the the NSM Slack channel, and basically in pretty much any other conversational venue. It's one of the things I'm very passionate about.